So welcome to Electronics History, and you are watching the previous year question series of digital signal processing of the year 2023 and 24. So in this lecture, we will see all the 2-mark questions. Okay. So first question is here, describe the energy and power signal with an example. Okay. So you have to describe the energy. So these are the 2-mark questions. Okay. So describe the energy and power signal with an examples. Okay. So the energy signal is defined as x of n is a discrete time signal. Okay, the energy of E of a discrete time signal x of n is defined as E equal to summation of ne minus infinity plus infinity x n square. Okay, similarly, this is called energy signal if and only if energy is finite. Finite means it is between 0 to infinity and power is 0. Then the signal is called energy signal. So a signal is called energy signal if the energy is finite and power is 0. Okay. For example, these are the examples of the energy signal. This is actually x of t. Okay. So these are the continuous time signal x of t, e to the minus 3t, u of t. This is a means energy signal, but it is a continuous domain. This is a discrete domain. So these are examples of the energy signals. Okay. Similarly, power signal, the average power of a discrete time signal is defined as, this is the formula for finding out the average power. Okay. So a signal is called power signal if the power is finite and energy equal to infinite. Okay, so if the energy is infinity and the average power is finite, then it is called the power signal. Okay, if the energy is infinite and the power is finite, then it is called the power signal. Okay, if power is finite, then the signal is called the power signal. Okay? So these are the examples of power signal. So these are the discrete time signals. Okay, so this is a continuous time signal. So these are the examples of a power signal. Okay, so you can write this way. Okay, so these are the 2-mark questions. This is a 2-mark questions. Second one is your this is the, what is the Vivo reference to the stability of the systems. Okay, Vivo means the bounded input and bounded output. Okay, so let us see that a arbitrary relaxed system is said to be stable if and only if for every bounded input that produces a bounded output. Okay, so if we provide a bounded input, the output will be the, if the output will be the bounded output, then it is a stable system. If for the unstable system, for bounded input, it will provide the unbounded outputs. Okay, so for this is the stable system. For every bounded input, if it produces the bounded output, then it is called the stable systems. Similarly, for some bounded input signals, if the output is unbounded, okay, that is infinite. Unbounded means infinite. If the amplitude goes to infinity, then it is the unbounded. Okay, so then the system is unstable. Okay, so bounded means the amplitude of the signal, okay, is less than infinity. Okay, and if the for any bounded input signal, if the output is unbounded, means if the amplitude goes to infinity, then the system is called unstable systems. Okay, so let us take some examples. So for bounded signals, these are the bounded signals. Okay, to test any system is stable or not, first we apply the bounded signals as the input, then see the output whether it is bounded output or not. If the output is bounded, that is called the stable system. If the output is not bounded or unbounded system, then the system is called unstable systems. Okay, so let us take an example. So I of n equal to x of n minus 5. Okay, let us test this signal whether it is stable or not. For that, x of n we provide as u of n. Okay, so y of n equal to what, u of n minus 1. So u of n is a bounded signal. We are applying as a bounded signal. Okay, so let us see the output is bounded or not. So u of n is a bounded signal. Okay, so y of n equal to u of n minus 1. So n minus 5 will provide by means advancing the signal, that is the delaying the signal by 5 units of time. Okay, so this is our u of n minus 5. Okay, so in this case you can see means this is also the bounded output. Okay, because the amplitude is never goes to infinity, it is always 1. Okay, so therefore this signal is a stable signal, so it satisfies the Vivo criteria. That is why this system is a stable system. Okay, so that is how you test whether a system is bounded or unbounded, means stable or unstable systems. Okay, let us take our third question. So what is a zero padding? So what are its applications? Okay. So zero padding means we are appending zero at the end of the signal. Okay. So let us, for example, x of n equal to this one. Okay. So how to pad the zero? So by appending zero at the end of the sequence. Okay. To increase its length. So you can see. So x of 0, x of 1, then you can pad 0. Okay. So these are the how your zero padding is done. Okay. Suppose you can see, suppose the signal is x of n equal to 1, 2, 3. Okay, so 1, 2, 3, and h of n equal to or 1, 2. Suppose you are doing circular convolution. So that is where these two signals should be of same length. Okay, so you have to here append a 0 to make the two sequence of the length equal. Okay, so here x of n and h of n both sequence having the same length. So for that you have to pad 0 or appending zeros. Okay. So that is the appending zeros at the end of the signal. So this is called the zero padding. Okay. Now these are the applications of zero padding. So it improves the frequency resolution in case of DFT. It is used in FFT computations and it avoids the circular convolution overlaps. So these are the applications of zero padding. Okay. Next question, what do you mean by Tudel factor of DFT? So how it is cyclic? Okay. So this is the Tudel factor. This is Wn is equal to e to the power minus j 2 pi by n. Okay. So it is the property is the cyclic in nature. This is the property which is called the cyclic in nature. So Wn k plus n, which will be Wn k. Okay. So this is called the cyclic nature. Okay. Suppose we have n equal to 4. So n equal to 4 means the length, the period of the signal is 4. So we can see W, that is the W5. You can see W of 5. So it will W5 equal to W of means 1. Okay. So W of here K equal to 1. Similarly, you can see W4, W for 0. So it will be, so N over N equal to 4 here. Okay. W for 0 equal to W4. So whatever the value of W4 to the 0, it will be the same as W4 to the 1. Okay. Because it is Wk. K value is here 0. Okay. So k value 0 means it is 0 plus 4. Okay. So it is equal to W 0. So similarly, so on so forth. So it is 6 means it would be W4 to the 2. Okay. So it repeats. Okay. So that is, this is known as your cyclic in nature. That is why it is known as cyclic. Okay. So we can prove this. Okay. So Wn to the power of k. So we can have here Wn to the power k. What is Wn to the power k? Is e to the power of minus j 2 pi by n. Similarly, to the Wn to the power of k plus n. So you can replace e to the power of minus j 2 pi. So this is k. Okay. 2 pi by n into k plus n. Okay. So you can cross multiply this. So it will be minus j 2 pi n divided into k into e to the power minus j 2 pi divided by n into k, sorry, n. Okay. So n can cancel out. So you can get this term equal to 1. Okay. E to the power of minus j 2 pi equal to 1. So you can get e to the power minus j 2 pi by n into k. So it is nothing but Wn to the power of k. Okay. So this is the property which is known as a cyclic. Okay. Cyclic in nature. So we have shown how it is cyclic by these derivations. Okay. So this is our Tudel factor. Okay. So it is periodic with period n. Okay. So what is frequency wrapping? So next question is what is frequency wrapping? Okay. Frequency pre-wrapping effects. Okay. So you can see in bilinear transform. This is the when we design the IIR filter. Okay. So we are what we are doing is we are mapping from j omega axis into the unit circle in the Z. Basically, we are mapping from analog to digital domain. So in this bilinear transformation. Okay. So in this case, the mapping is non-linear. That is why lower frequency components are expanded, where the higher frequency components are compressed. Okay. So in bilinear transformation, this is the formula for means mapping from S domain to the Z domain. Okay. So now this non-linear mapping process causes the frequency distortion. Okay. So in this case, there is a pre-wrapping. Pre-wrapping means because of non-linear mapping, so you have to adjust the annual frequency omega p, that is the in analog domain before transmission to match the desired frequency in the digital domain. Okay. So this effect is known as pre-wrapping. Okay. So next is then state the time reversal properties of DFT. So you have to only the state the time reversal property of DFT. Okay. So if the endpoint DFT of x of n equal to x of k, then the endpoint DFT, that is the of minus n. So it is called the modulo n actually. So it will be n minus n, which DFT will be this is the minus k of modulo n. So it will be x of n minus k. So this is the time reversal property of the DFT. So in this question only the statement is required. Not we are not going to prove this. Okay. Next question is here in endpoint FFT. So how many complex addition are required? Okay. So number of complex addition in required in endpoint DIT FFT. So you can see actually the in FFT it can be DIT FFT or DIF FFT. Okay. So both are in both cases the number of complex addition are n into log 2 n. Okay. This is the formula for finding out the complex addition. For complex multiplication it will be n by 2 log 2 n. Okay. But the question asks only for complex addition. This is for complex multiplication. Then what is the reason the FIR filter are always stable? Okay. So for FIR filter, this is the y of n. Okay. So you can see in this case, this is the finite impulse response. Okay. Means this should be finite. H of n equal to finite. Okay. So that is why we are getting some stable system, because where the amplitude here is less than infinity. Okay. Means this is the bounded. Okay. So in this case, this is the bounded case. Okay. So in this case, that is why the FIR filters are always stable systems. Okay. These are always Weber stables. Okay. Next question is state the characteristics of adaptive filter processing. So these are the characteristics that adaptive systems that adapt the parameters automatically to minimize the error. Okay. Similarly, it uses the error signal to update the filter coefficients. It is a time varying systems. Okay. And it has the algorithm. It is a least mean square and recursive least mean square. This is the algorithm used in the adaptive signal processing. Okay. So applications are noise cancellation, echo cancellation, and system identifications. Okay. So last question will take. So what do you mean by mean square error? Okay. So it is in the adaptive signal processing. So mean square error, error signal is defined as E of n equal to D of n. This is the desired signal. This is the output Y of n. Okay. This is the desired signal. Okay. This is called the desired signal. Then, so what will be the means mean square error. So mean square error equal to MSB equal to expectation of this error signal square into n. Okay, not into n, e square n. Okay, so this is the mean square error where we can find out by e is nothing but this one. Error signal is dn minus of y square. So e square n it will be square. Okay, so this is our mean square error. Okay, so this is used for performance in the adaptive filter. Okay, so in this case we have seen all the short type questions in the year 2023-24. Okay, so next class we will see some 6 math questions. Okay, so these are our reference. So thank you for watching this video. If you have any doubt, you can free to ask me in the comment section. Okay, so thank you all. So have a nice day.